There you go. Okay. Yeah, thanks everyone for coming, and thanks to Hanchi, Alvaro, and Charlie for inviting me. I'm very happy here today to talk to you about causal inference for social sciences. First, I would like to thank my collaborators, without whom this work wouldn't be possible, and especially shout out to my advisors, Arthur Greta and Matt Kusner and Ricardo Silva, who supported me a lot during this project. So, I want to start by giving you an overview of this talk. I will start by motivating the problem of causal inference for social sciences from three aspects. What we want to achieve with causality, why is causality suitable for social sciences, and then I will describe the characteristics of social science data and the specific challenges associated with it. And then following this motivation, I will outline three specific methodologies which aim to solve to begin to solve some parts of the challenges that arise from social science data. Okay. So so what we want to achieve with causality, I have only a one-liner for this. So in like briefly, what we want to achieve with causality is to have a metric to compare different actions with respect to their effects. So this is exactly what we want in social science. We want to ask about how would different actions impact various outcomes of our interest, and we want a good metric to measure this. So why is causality, like this framework, suitable for the study of social sciences? Why don't we use a different thing like deep learning to learn models and then compare using the predictive model that deep learning gives us? So to answer this question, I want to take a slight detour and first give you a brief introduction of causal inference in case some of you are not already familiar. So I have this example where I'm at a school, and the educators of the school want to ask about the impact of grade retention on cognitive outcome of students. They want to ask about this edge here. But of course, grade retention and cognitive outcome have like this common cause variable, that's cognitive ability of the students. So by grade retention, I mean like making the student repeat grades if they're not performing well in tests. So a student who is like maybe have higher intelligence in some sense would both be less likely to need to repeat grades and more likely to have cognitive outcome, right? So there is this common cause variable that causes both of them. There's a correlation that's like via the cognitive ability variable. So this is what we don't want. So in one way, the study of causal inference is about disentangling the causal path, which is directed path from A to Y, from the confounded path, which is the backdoor path that's via cognitive ability. So you can see that there is an arrow into A. So this is like, typically this is the path that we don't want. So more formally, the target quantity that I want is described in this slide. So I have some observed data triples, A, U, and Y. So what this is telling us is the observed data comes from like sampling repeatedly from this three variable world, right? So I'm in this 3 variable world. I have some common cause variable U that's like the source of everything. I will like discuss this oversimplified structure later. But for now, I have this U that like generates everything, and then A comes from U, and A and U then come from Y. I repeat this process over and over again. That gives me my observational data. But now I want to imagine that different to what I observe, I want to say that I have an action, an external force that's going to change this A. It's going to set this A to a particular value. Let's say little a. And I want to ask, and what I want to ask about is like, what would happen to Y on average if I set A to this little a value? Of course, Y is still influenced by U. So that's why like often what we're interested in is the average value of Y given as A. But however, I don't want to actually perform this experiment because let's say, so that would be like forcing everybody to repeat grades and then observe their cognitive outcome. So that's obviously a harmful thing to do for a lot of students. So we don't want to do that. So what we want is we want to find out this quantity expectation of Y given to A when we only have observed data. So how can we do this? A warm-up is to consider observed confounders. So when the U is observed, when the U is observed, this is rather easy. So when so what I can do is this. So observe that the generative mechanism from U and A to Y in both the observed case and the intervened case are the same. So when you like set this A to a different variable, like this part of the graph is the same, right? So what I can do is I can run a machine learning algorithm that'll fit a model from U and A to Y. And once I have this model, and if what I want is the average impact of doing A on Y, then I average this over the marginal distribution of U. And the reason is in the intervene case, which is the desired case, there is no edge between U and A, right? So doing A doesn't do anything, given A doesn't do anything on U. So I'm averaging over the marginal of U. So this is sort of like the vanilla algorithm. There are various problems that we'll discuss later, but you can at least be convinced that kind of, in principle, if you can do this perfect regression, then this problem has a solution. So now what if the confounders are not observed? Then there's a problem because we can't just run a machine learning algorithm to fit from U and A to Y. So what do we do with unobserved confounders? I want to just introduce one more classical algorithm, which is identification with instrumental variables. So this scenario requires me to have an external, an external force that's going to impact A, except this is not a perfect intervention, right? So Z doesn't set A to a fixed value. It doesn't have full control of A because there is still an edge into A from U. But what's important is that this Z is independent of U and some other conditions that I'll introduce in a few seconds. So, but basically, if I have this Z variable that's like external, so this thing could be, for example, if the school makes so if like A is like scientific ability and Y is their skills to make money, then Z could be like the school enforces this education policy that makes that says in class teachers need to spend X percentage on doing scientific projects. So this is not a perfect control because students can still be ill or they don't want to, they're like bad students and so on. So the teachers don't have full control in like making them do these scientific experiments. But this will of doing this policy of doing scientific experiments, it's like independent of the other attributes of students. So if I have this structure, then I still need to assume that the generative process from A and U to Y is an additive one in the sense that U is additive. So I need Y to be f of A plus some noise U, assuming the noise of U is, the expectation of U is 0 and U is independent of Z. If I have this, then I have this identification result that f of A, which actually, so before that, f of A here, it would just be the causal effect because like if when I average out U, I just get a f of A left. So here, the target treatment effect is just f of A itself. And how do I identify this f? It turns out that there is this identification result that says f would satisfy this integral equation. So if I regress Y to Z, that's the same as basically regressing f of A to Z, which is what this thing is doing. So the integral is just saying the integral is just the expectation of f given Z, right? So do you see this? Yes.
This kind of expectation of Y given A, is this equivalent to delta P models of causality from like the 90s?
I'm not sure.
Essentially change the probability of so much.
Yes. So you can view it like that. Yeah. So when you ask about interventions, that's so what you're essentially doing is you first need to start from a graph, and then start from this graph. You can factorize the graph using using graphical conditional independencies. And then what interventions are doing essentially is just you take one of the factors which you view as an independent mechanism and then you replace it with something else. Yeah.
But then one thing that this doesn't capture is the strength of the causal weight between A to Y, right? So this is something that have the PowerPC model of causality from Chen kind of criticize the Duffy model with, because you don't really measure the strength of causality, right? You just measure the likelihood of some cause and really how strong the relationship there is, right? And this is something that's really important in social sciences. You want to be able to measure the strength of that base, right? If it's really small, then it might not be very reliable, might not be a dimension that's really useful. Right?
Okay.
You want something that's positively strong. Right?
Okay.
So this doesn't necessarily measure the positive strength.
Right? The delta P model, right? Oh, I see. Okay, thanks for pointing that out. Okay, great. So yeah, if you're not familiar with this, then I have a linear case that makes it very clear. Basically, in the linear case, Y is just some linear combination of A and U. U is still independent of Z. And again, in the linear case, A is also a linear combination of Z and U. Then you can see very clearly that you can just you can substitute for the A, right? So you like do some change of variables and then you substitute it in, and you would realize that Y is just beta gamma times Z plus this thing U. And then your goal here is, of course, to identify the beta for the F of A. So so what you need to do is you just need to regress Y onto Z to identify the beta gamma, and then you regress A onto Z to get the gamma, and then you just like divide them to get your beta. And this is what like basically solving this inverse, like inverting this integral is doing in the linear. This is the linear analog. Okay. So warning, and the reason that this is a classic algorithm that we want to extend is that this is subject to strong assumptions. So one is that you need to assume this additive error model, right? This like plus U is important to like for us to get rid of it when we take the average. And also, more importantly, aside from this second condition is just saying Z is independent of U in this graph G. Oh, sorry. Yeah, the second one is saying Z is related to A in this graph G. But what's more important is that this in this for a variable to be a valid instrumental variable, an IV, A needs to capture all of the causal influences from Z to Y. So if I remove A, then Z has nothing to do with Y. So this is a strong assumption, and I will illustrate by giving you an example. So yes.
So can you explain the installation?
Yeah. So G refers to this current graph G, and G sub A bar means the graph where A is removed. Sorry, the graph where all the I think outgoing edges from A are removed. So the second one means Z is not independent of A in this graph. So there is an edge. And the third one means that if you don't count A as a mediator, then there is no causal path from A to Y. So A needs to be in all of the causal paths, all of the directed paths from Z to Y.
And the explanation point is the negation of the.
Yeah. Explanation is like not independent. Yeah. Okay. So so why is this strong? So for example, in economic studies, it has been the case where multiple papers use rainfall as an IV for 3 different actions. So we immediately know that at least one of those papers, at most one of those papers are correct, because they can't all be correct. Because if they're all correct, then you would have Z rainfall going into 3 different actions. So you would already have, if this is a true action, then there are like these other paths that go into Y, not via this A.
Why can't there be other actions that also go to Y?
Oh, because like if there are other actions, so if instead of this additionally to this A, you also have like a bar, that also has like Z goes into this other A into Y, then like already by violating this assumption, this A, for example, this Z cannot be a valid IV for this A, because if you discount the causal path that go via this A, there are still other causal
Okay.
paths.
I mean, the real world could have other A's, but this framework statistically can't allow other A's.
Exactly. Yeah. So that's why this is only a classical algorithm.
But
That's
those are the
yeah.
papers that find different A's. They
Mhm.
could be correct because you can get the A's involved. They just
They could be correct, yes, but they're not using this method correctly. So yeah, so the causal effect they're finding using this method would be biased, right? Yeah.
So just for clarification, using 3 papers with 3 different routes to Y.
Well, 3.
Paper with 3 routes.
Oh, it was no different papers.
Okay.
So no different papers each have one route, but the routes are different.
But that's fine.
Yeah.
It's just consistent.
No, it would mean that, so if all of them are simultaneously correct, that means at most one of them is correct, right?
No, it's this framework can't handle that situation. where you can-
Oh, but the thing is, they have all like found these variable pairs, rainfall on one thing, rainfall on another thing. That's okay. What's not okay is they all used instrumental variable method to correct for the causal
So this
effect.
method is incorrect because there could be other causes, other ways to define case Y.
Yes. So yeah, so this method only holds if you know for sure that, like, for this rainfall variable you found, A is the only thing that goes, A is the thing that'll intercept all of the paths from this IV to the thing. If there exist other A's that's different from your current A, that goes like such that you can have Z goes into this other A into Y, then you can't use this method.
So from a constructive point of view, these are characteristics.
Yeah.
I have understood. If you're in this setting where you want to find an instrumental variable, then you're forced to look for one that's extremely precise
Yeah,
with effects, so that it doesn't drive through multiple paths towards the
Exactly.
target variable.
exactly. Yeah. So this is why this method is is very restrictive. And another problem is, of course, this problem often come with weak instruments, right? So as you say, if you have like a very tangential variable, like rainfall as your IV on, and you want to have A as like GDP or something, then that's already a very weak variable. And this situation often co-occurs with like the IV is not even valid. So there are other things. Yeah. Okay. So so this is the example that I just gave. So in this paper, in this talk, we will discuss ways to relax this IV condition to allow for some dependence with you, so you can still use the method validly. Okay, so that's a brief introduction of classical causal inference. Then now I want to argue on the high level, why is causality suitable for social sciences? So social science is often considered decision-making for positive impact, and this is exactly what this is doing. So I want to consider doing making a particular decision that's different from the ones I'm already making. And this is well, some people call it the counterfactual, but it's really the intervention. And the significance is that you're trying to ask about something that you haven't already done. And moreover, social science is a high-stake domain. So we should try to use observational data rather than perform ad hoc experiments. So if I want to ask about what would happen to make all the students repeat grades, then instead of actually doing that, I would like to just use my observed data sets where some students are repeating grades, some students are not repeating grades, subject to their intelligence level and whatnot. So I would rather use that rather than making everyone repeat grades. And also, again, in this example, there is this spurious correlation that arises from different academic capacity of the students. And we also want to correct this by causal algorithms. So, and now at this point, you are probably wondering, surely the scenarios I have just described are extremely simplistic. They're extremely unrealistic. So is like, why should you believe that causal inference is even useful if this is all I have, right? But before I go into that, I want to like drill this point further by discussing more the characteristics of social science data that like the examples I just gave are not compatible with. So in social sciences, the observational data are typically generated from an unknown graph. So I can't say there is this like 3-variable graph that like the data, I match this data to this node and so on. And also it's like, generally not possible to perform randomized controlled trials to identify the graph. It's generally not possible. We don't have the means, right, to perform randomized experiments to identify edges and then construct the graph like that. However, without graph, we can't compute treatment effect. So it's like a chicken and egg problem. And like an example, just to illustrate point, it's still a simple example, but just to illustrate the point of the difficulties of identifying graphs from observed data is that, like, for example, if you have these two graphs where like the red edge is oriented differently, there is like no way of telling from observed data how this edge should be oriented, because both of these graphs, they so if you're familiar with Bayes nets, they encode the same set of conditional dependencies. Yeah, so they both say everything is dependent of everything else. Well, actually, yeah.
But they have a different, like,
they have a different factorization.
yeah, they would have a different kind of characteristic structure, and if you were to define the processing, you would have different results. Or is that if you were to generate data from these graphs,
it would
exactly the same simulations?
Yeah, I believe so. So if you get data from like various configurations from these two graphs, you would get exactly the same set of data. So if you start with data wouldn't be able to tell you which two graphs you
But
should
you
get.
start with these two hypotheses, of two graphs, and you generate data from those graphs, right? Based on some graph hypotheses, you would get exactly the same results. I found that a bit hard to believe.
I believe that's true because, well, take another example. If you just have two nodes, A cause B and B cause A, you can't tell without doing experiments which way around it should be oriented without some assumptions, right? Yeah.
This seems right to me that when you have the definition of dependencies, but it also seems to be relatively simplified example in terms of usually you collect all of this data in time.
Oh yeah, that's a good point. Yeah.
How can it be like, how do you incorporate this in this framework? Because that's actually something you usually have access to, right? Yeah,
that's a very good point. So if you have already some heterogeneity in data, so you don't, yeah, so what that means is like when you say collected in time, then I think what you're implicitly saying is like at different time points, graphs are a bit different. So you're actually getting data from slightly different graphs, from slightly different graph structures. And then you can use it to identify.
I'm not sure that that's what I was thinking about. I was rather thinking about the fact that you have these variables as time series, and hence you can exclude some directions based on when so alignment and causality when effects are happening. Is this something that would help you out in this case, like same graph, but you observe values as well?
Yeah, okay, sorry, yeah, I shouldn't have said different graphs, but same graph, but like how should I put this? Like different levels of instantiation of some variables. That's what you mean, right? For example, like that would be like, you know, you kind of repeat this graph many times, and then at different points, you'll like at time 1 you would have a certain revision time. At time 2 you have a different revision time, and then you collect data like that.
I think that the point is simply that
causes come before their effects. So if you observe one variable took its value at some moment, another variable later, then you can infer directionality from that.
Oh, okay.
Aptitude doesn't really have.
Okay. Sorry, I misinterpreted the question. Yes, so temporal reasoning is definitely a way to infer directions. And I will get to this point later. I guess you can do this in, I'm not sure how you would do it data centrically, but usually this temporal reasoning is used as just a philosophical framework for experts to infer directions.
Okay, let me rephrase the question. I think I'm getting closer to what you said about different graphs. If I have all of these variables recorded as a function of time, then I could potentially build a stack of graphs, one graph per instant in time, and then so a stack of nodes, and then I will only have connections from like directional connections that will be flattened in this case from, for example, aptitude at t -1 to some results at t.
Yeah,
so
okay.
This is the only way I can imagine to grow this static framework to incorporate time.
Yeah. You can certainly do that, but when I said you can use like heterogeneity between graphs to do causal discovery, I just meant that it helps you infer this edge if you have some independent variations on the variables. So if you want to tell if revision influences aptitude or aptitude influences revision without reasoning about temporal, without reasoning like temporally which one should come first, then if you have data where like temporal changes, where aptitude changes independently and then revision changes with that, then that helps you infer it should be aptitude to revision. But if you have data where revision changes independently and then aptitude doesn't change, so that also helps you that it doesn't go the other way around.
When you say revision changes independently, what do you mean independently?
So this would be like, so this example wouldn't really work, right? Because we can't just like tweak one's aptitude. But imagine that you can, like you're like this really powerful being that can just change one's IQ. Then you would be inferring this this direction by this all-powerful being basically independent, like changing externally, setting this attitude to different values, and then you observe that revision changes from that.
We are out of observational and interventional.
Yes, but sometimes in data you have this external thing. So when you have I don't know, data Amazon collects or something, then at different times the user are doing different things. So you can say that this is like an external, this is like an experiment, like maybe not without full compliance, but it's like an experimental component. Yeah. Okay. Yeah. So depending on in the fully observational case, these two DAGs are not like distinguishable. And the problem is the problem is now that they give different causal effects. So in this stack, the causal effect is just the only directed path is that one. Whereas in that DAG, there are two directed paths, right? So the causal effect is different. So you have a problem where you can't get the graph from fully observational data. There are multiple graphs compatible with observational data, and these different graphs give different causal effects. So this is the case where you can't really identify the causal effect. And of course, in social science data, the graph is a lot more complicated than 3 variables. So you have so this is just an illustration where like you might want to ask about how does family income impact exam results, and then you have a bunch of things that impacts family income and exam results, so a bunch of confounders, and you also have some aptitude like as mediators, but then like how you certain these are like all of these connections are definitely right, so for example, does diet influence the exam results? Or is it the other way around? Like in some cultures where if you get better marks, you get like a reward for having something nice. So this is to illustrate the difficulty. So now the second point is that when you have in social science data, there is typically low signal to noise ratio. So when so we will have like, how do we measure mastery of a subject? We can do it via test scores, but that's only a measurement and debatably with high measurement error, right? So, and what measurement error can do is that it can mask interesting relationships in data. So an example I have here is, so skill mastery to exam results. We would probably all agree that the causal direction would be mastery causes exam results. So I observe exam results as a proxy of mastery. And now now let's say if I want to infer how does mastery impact career outcome, where career outcome is okay, like I'm assuming it's observed here, but generally it would also subject to some proxy, but for the point of illustration, assume this is observed. And let's say there might be some confounding here, I don't know. And so if I just simply ignore mastery and use exam results to act in place of mastery, and say I have some perfect spurious correlation correction algorithm, I just simply replace where it should be mastery by exam results. Then what would happen is what would happen is illustrated in this graph. So the pink line is it's a simulated example, but the pink line is the structural function so the true relationship from mastery to career outcome. And because like this and then the green line is done by using exam results in place of mastery, and then feed it into this consistent structural function estimation algorithm. Then what happened is that it smoothed out the curves in this in the pink line. So in this particular case where I generated this graph, this is intuitive because the measurement noise in exam results is additive. So you can imagine like squiggles in the horizontal direction, like it smoothed out the curvature in the true function, in the true curve. And and the red line is the one that I'll introduce later, but you can see that it corrects it kind of fits the curve a lot better. Yeah.
So what is KIV?
KIV is a provably consistent algorithm that can deal with confounding when you have both observed mastery and observed career outcome. So this is a simulated example. So KIV is kernel IV regression, actually. So in that simulated example, all of the assumptions are met, except that mastery is just replaced by exam results as a proxy. And you can see, yeah, it smooths out. Yeah.
That's why at the very left side of the red line, as you decrease the X variable, you actually increase Y in contrast to the two data. So in this way, that seems a bit inaccurate. As you go from, for instance, like 0.1 on the X variable to 0.0.
Oh,
0,
yeah.
Increase Y, right? And why would you get that result?
Yeah, you're saying like why does the graph curve go? Yeah, so this is the problem with the this is like an idiosyncrasy of the method. So basically what's happening is when there's high data density, it fits quite well. When there is some
Is there a prior in the model?
No, it's not Bayesian. No, it's not Bayesian. But it's just that when there's high data density, there's just more data points. So it's easier. So the variance is lower, I guess. But then when there's fewer data, it hooks up and down because of the choice of kernel. So it's a Gaussian kernel, so there are all bumps. So when there are not enough data, then yeah.
So I would be very interested as we proceed.
Yeah.
It's possible to pose restrictions on, or like maybe in addition way, maybe not, on these kind of functions. For example, in this case, we would have help to say, well, I know this must be monogamous.
Right. Okay. Yeah, I guess you can try and impose that restriction in your search space, in your hypothesis class. Yeah, but I am not sure. Yeah, we can discuss later. Okay, so now the third point I want to make is in social science data, the data, it can be high dimensional. So again, it wouldn't just be a 3-variable case where every variable is univariate. And when there is high dimensional data, even when confounding is not a problem, we're still subject to this thing called regularization bias. So this is an illustration. So imagine if you want to fit a high dimensional variable X to Y, then your black box algorithm might ignore this one colored in this one feature colored in orange, which let's say is like a binary variable, because like the variations in the other ones is already account for Y, already enough to account for Y, right? So now if you want to ask like, what happens to Y when I arbitrarily vary this orange node? This black box algorithm is going to tell you no difference, which might not be true. And lastly, there is confounding in social science data. So the examples I have is, let's say, for example, aptitude or socioeconomic status. I'm sure you can find more examples than me, and yeah, so it would be great if you can tell me more examples in the in discussion period. Sometimes the confounding is not observed, which is also what I already illustrated. I just want to illustrate a more well, Simpson paradox, which if you haven't heard of it, I think is a very crisp way to make this point. So here again, in that same example, I observe repeating grades and I observe exam results, but I don't observe aptitude. So if I simply do a regression from repeating grades to exam results, or some other 2 variables with unobserved confounding, then in the worst case, I can get something like this. So in the graph on the left, I'm just simply regressing from A to Y. So because and then the 2 clusters are due to my unobserved confounding. So let's say it's a 2 category 1. And that's why you have 2 clusters, but then overall the trend looks downwards. But then if you fit a curve to each of the cluster, they both go upwards. And if you now average over that, take the marginal, average over the marginal distribution of U, you should find the true causal effect is, the true causal correlation is positive, but in the other one, you actually find a negative coefficient. So you would get like an opposite effect, which is quite bad. Okay.
It's not actually a lot of regression. It's the conditional estimation. And if you did the conditional estimation, the solution to the estimator, you get 2 regions. And so you do not see this problem.
Yeah, okay. So this is a problem where I guess you assume it's linear. So you're doing a linear regression. So you would do that. But okay, I see your point. If you use a sufficiently expressive function class, then you'll get 2 ridges.
No, I think so.
Yeah.
I'm afraid just positing a better function class doesn't fix this, because there are no functions as in mathematical functions that map 1 to 1.
Yeah. Okay.
That can represent this data, right? That you would have to have 1A assigned to multiple Y's.
Yeah. Okay.
For the function. So there you actually need a multimodal density to represent this.
Mm-hmm.
Of course, the question is, what do you do with the multimodal density? When you have it, it's much harder to interpret, but it would accommodate perfectly the situation. You have 2 ridges, and you have this paradox. So I'm not sure how much. I mean, I know I have read in the headlines like Simpson's paradox is something in causality, But how much is you do concentrating on expectations as the way you process effects as opposed to frequencies?
Well, if you I think the problem is inference. So after you fit this multimodal density, you still want to conclude something from it, right? So what are you going to conclude from it? You still would, if you still take like the average of y given a particular a, then you would still end up with this problem.
So what you put, if you condition a particular a, you will have two bars. So you
and what
you have a determinant, so you say, okay, if I instrument or if I fix action A, I may have due to a hidden compounder any of y1 and y2. That's,
so you're still acknowledging
that's ignorance, but that's calibrated. So I agree that this doesn't tell us like what we should do, but it is not as terrible a situation as with expectations.
Yeah, fair enough, but it's not so terrible because you acknowledge that there might be some hidden confounding.
Yeah,
right.
Maybe
okay.
Actually, this modality is the thing that we're missing.
Yeah, I agree. Okay. So so I identified 4 problem themes: unknown graph structure, measurement noises, confounding, and high dimensional data. I think this is a good point where I pause recording to take some questions. So now I want to introduce some algorithms that attempt to address some of the issues that I identified. So the first thing I want to talk about is unknown graph structure. So actually, for this particular one, I don't propose an algorithm, but I want to make a few points. So although it's true that the graph structure is generally unknown in social sciences, what I don't think is true is that no causal claims can be made without knowing the full graph. So partial claims, so the first point is that partial claims about the graph can be made with reasonable confidence. So for example, we can use temporal reasoning that aptitude should probably cause, I think it was result, the like exam result is something I used before, rather than the other way around. So we can use it using, we can infer it using temporal reasoning. We can infer it using expert knowledge, which essentially, which partially comes from years of experience and performing a collection of experimentation. Or we can perform some experimentation that we think we can afford to do to infer some edges in the causal graph. So here we can probably conclude with reasonable confidence that it should go this way rather than that way. And in some situations, the partial knowledge of graph structure is enough. And for example, in one of the methods I will introduce, we just need to be able to group various like imperfect measurements of the confounding into 3 different categories. And once we can do that, we can infer the causal effect with respect to this proxies. While the structure among the grouped proxies themselves don't matter. So you don't need to know the graph, the causal structure among the proxies. And so because of this, just because we're starting from a graph doesn't mean we're making strong graphical assumptions. And the second point is I want to acknowledge that it is an assumption, but I also want to point out that we always have to start from some assumptions. So just because we're using a structural learning algorithm, for example, to try and learn the graph from data, that doesn't mean we're suddenly making no assumptions. Rather than instead of that, the structural learning algorithms actually also depend on their own meta assumptions. So you also need to, like, for example, specify some function class. If this is ill specified, then you're also not going to recover the true graph, right? If your true graph just like doesn't even lie in the function class that you're considering. The strength of assumptions we need depends on the amount and quality of data we have. If you have very, very good data, then yeah, and if you have very good data and also what you want to say requires a rather elaborate graph, then you can try and do that. But if you don't have very, very good data, then you can't really hope to get a very good graph from it anyway. So you need to start from some experimentation or some more expert knowledge. And my perspective is that this causal graph semantics started by Perl is actually a good way of encoding expert knowledge. So the quality of results depends on the quality of data. So this is all I want to say for unknown graph structure. Now the remaining three issues that we've identified, I want to split confounding to unobserved confounding and observed confounding, and I'll deal with them separately. So for these 4 nodes now, I have worked on 3 different methodologies, each hoping to start to address one or more of them. So I will start from generalized Robinson decomposition, which aims to address high-dimensional data and observed confounding. And then I'll try to relax observed confounding and to talk about by talking about proximal causal learning. And finally, we also further relax this observability condition from just unobserved confounding to also that the treatment is also corrupted, and that's where I will talk about the third method. So generalized Robinson decomposition. So first I want to say something about the assumptions and usage contexts. So this method is useful for when you have high dimensional data. For example, you might have practice essays. You might want to start from some practice essays from students that you collect, and then you want to use it to infer like how they're going to do in the English exam or something. And then you also have past teachers' reports, which is also in text that you collect that like hopefully should tell you something about that hopefully it should tell you something about the quality of their essays and also how they're going to perform. So you have this need to process high dimensional data, like you might have to do some NLP. Yeah.
Excuse me, this might be picking, but
yeah.
When meaning of causality, it isn't like choosing the language with something like past performance according to teachers, like the reports cannot cause the results, right? Can they?
Yeah, so that's a good point. So past teachers' reports are really a proxy of the students' like skills in writing. So this method indeed doesn't deal with that. It doesn't deal with the fact that this past teachers' reports might only be a not so good proxy of their skills.
When you use the word proxy, do you equate that with instrumental variable, or is this other nuances? Like, is it X controlling something else that quite closely mirrors their writing practice or writing ability assessed in past periods of time?
I'm not sure I understand the question.
Yes, so I'm just trying to connect. Like you're saying now, okay, past teacher report actually is not what we should put here, but that's what we have. It's a proxy
of the writing skills, let's say. Yeah.
So X should actually be the writing skill. If I could draw this graph, then X would be an unobserved writing skills, and then I would have some C, which are the reports that I do or I could observe.
Yeah.
I'm just asking if, from a logical point of view, this is fits with the description of the data of an instrumental variable.
No, it doesn't, because first of all, the instrumental variable should have nothing to do with the compounder. The IV should just be something that influences practice essays. That doesn't, yeah.
Because it's here is that.
Yeah. Okay. So so there is nuance here that can you really use past teachers' reports as a proxy that's like good enough to run for this compounder? So so this, it could be, or it could not be. Maybe like the teacher's reports are so precise that you might as well just use it as a precise description, or it's not. But this is an assumption. And you should use it if you have good faith in teachers' reports. And a word is, I just want to say, like, just because the graph is drawn with 3 variables doesn't mean it's only compatible with data sets where there are only 3 variables. So what the graph means is just that first so if you've identified your treatment and effect pairs as practice essays and exam results, then what you need is this 3rd variable that's that counts as a sufficient adjustment set, which is the confounder. So, for example, if like, in addition to practice essays, exam results, and past teacher reports, you also have some other variables that follow this structure, then then past teachers reports is still a valid variable, such that if you adjust based on its marginal distribution, you recover the full causal effect, even if you might have some other variables. So by this, I just want to say, just because we draw 3 variables doesn't mean you only need to have you can only have a very simple graph. So the usage contexts are this method deals with data in arbitrary forms. So you can have text, you can have images, low or high dimensional data. The point is you can use a black box algorithm to process these. But then later we introduce a framework that can ensure that you still have fast rates, even though you use some black box algorithm to do some pre-processing. This can also take continuous data or data with many categories, which is different from previous algorithms, which only takes like generally binary variable or unidimensional continuous data. So an example I gave is different lengths of revision time. I would appreciate more realistic examples from the audience. So this does require this condition called overlap. So what this means is that you need to, so for all of the features of A and features of X that you use, you need to observe all of the pairs, at least with some non-zero probability. So if there are some feature A and feature X pairs that you never observe, then that violates the assumption. And finally, this actually targets the conditional average treatment effect, which is that what is the average value of Y given both a given X and do A. So which actually just boils down to the expectation of Y given A and X in this particular case. Even though then it just looks like a standard machine learning algorithm, I will illustrate later that this could still be a problem. Yes.
I was just wondering, the overlap condition, is that similar to some of the positive support?
Yeah. Exactly. I'll elaborate on it later, but basically, yeah, you need to have positive support on features of A cross features of X. So why not just do regression, because you observe everything. So again, the one answer to this is this regularization bias. So recap to this previous slide. That like if you just do this regression from your I think A and X to Y, then like if your X, let's say, is much more high dimensional than A, then and basically contains enough variation to account to predict Y with high preciseness, then your algorithm might just ignore your A. So that wouldn't be very helpful when you're trying to infer treatment effects. So to deal with this problem, I'm going to first introduce this framework called Robinson decomposition, which is a fairly old concept. But basically, it allows us to construct a learnable objective of the binary conditional average treatment effect. So where you only have two treatments and you have a high dimensional confounder. So we need to define the propensity score as the probability of treatment being 1 given the confounder, given the user features. And then we define the conditional mean outcome, m of x, which is just the expectation of the outcome given the features, given the confounders. And then we partial out this m and e from our observations of a and y. So we take y tilde to be the original labels, but subtracting the expectation of it given the confounder, and then we take a tilde to be the treatment, subtracting the propensity score, and then we can yield the objective this tau b, where tau tilde b, where b is a b stands for binary. So this thing is the Kate function. So this tells us so if you input x here, this tells us what's the difference of taking action 1 and action 0 given this feature. And to do this, we basically just do a regression from a cross this, from a tilde I cross this function to, we do basically a linear regression, a regularized linear regression from this function to y. And we call m hat and e hat the estimated nuisance functions. Yeah.
So what does the cross nuisance? Is that like
I think it means times. So this is okay. So here this is just so a is a binary variable, right? So a minus the propensity score is some value between 0 and 1. So this like weights this weights this Kate effect. And then yeah. Okay, so this deals with the binary case, and because of the need to deal with continuous treatments, we generalize this to the high dimensional continuous treatment case. So for the so first we assume that we reparameterize the outcome surface as y equals this g of x is a high dimensional function of x. So it maps x, which is a high dimensional variable, to RD, where D is some big number. And H of A is a similar map. So with additive noise. So this decomposition has this nice universality property. So if we let the dimensionality of G and H to grow up to infinity, we can approximate any arbitrary bounded function in the in all of the continuous functions with domain on x cross A. So the conditional treatment, the conditional average treatment effect is simply just G inner product H at A prime minus G inner product H at A. Take the difference. So and then we're going to define these propensity features. So remember, we want to, just like in Robinson decomposition, where they partial out the propensity score, here we partial out the propensity features. And I'll explain why that's useful later. But analogous to that, I define the propensity features as the expectation of my features of A given X. And I recall that M is the same. M is just the expectation of Y given X, which plug Y in yields just the G inner producted with E superscript H of X. And then I follow the same steps as for the binary treatment case. I yield on the left-hand side, I partial out the mx. On the other side, I partial out this G inner producted with E of H. And then the solution is so I can learn my G, which together with H will give me my Kate, will give me my conditional average treatment effect, Kate, by doing this linear regression, basically from the partialed out Y to the partialed out right-hand side. Okay, so why is this decomposition useful? So in the finite basis case, so in the case where I say there is a fixed D of features that I will take, I can rewrite the structural function from my x to a, from my x and a to y in the following, right? In the fixed featured case, I can write them as just some fixed features of x inner producted with some features of a with this theta that represents my finite dimensional inner product. And
sorry,
theta. So theta is a matrix. Yeah, theta is this positive definite matrix that acts as the inner product. Yeah. So the f star here would be like the actual structural function, expectation of y given x and a. So y here would be decomposed as y equals f star plus noise, where noise is independent of x and a. Yeah. So yeah.
Could you also define like a uncertainty term for any like x star and star? Like this, here you're defining the expectation, right?
Yeah.
This kind of resembles the same form as a linear regression based on the top equation.
Yeah.
So could you not also define some covariance function?
Yeah, you could, but here we only did it in the frequentist sense. So you could there could be a Bayesian analog. Yeah. So what we can show is that if I learn this, so here under this decomposition, the previous learning problem boils down to doing this partialing out and then learning the theta. So if I use this decomposition and then learn this theta using by regressing the partialed out y's and the partialed out right hand side, then I can get then provided that the nuisance functions m hat and e hat h converge at only a slow rate that I will specify later, the target function converges at almost parametric rate, where this p can be arbitrarily small. So this is made clear in theorem 2 of the paper. So, and the rate that m hat and e hat need to converge in is n to the minus quarter rate, which is a much slower rate. And this requires the overlap condition on the features of x cross the features of t. So you have to observe all of the pairs of features x and t with non-zero probability. Okay. Yeah. So yeah. Oh, sorry. That's a typo. Features of a. T should be a. So thanks. So what does this mean? Yeah. So the target or nuisance functions never converge faster than parametric rate. Generally, they will be slower if you use like a neural network to fit it. And usually, this rate would cap the rate of the target function. See the discussion in this double machine learning discussion. So what we show is that in the fixed feature setting, the target function converges at most at least, sorry. So at like at least this almost parametric rate, as long as the nuisance functions converge at quarter n rate. Okay, so the practical algorithm is that in the first stage, you learn the parameters of this m hat theta. And then because this m hat theta is just the expectation of y given x, right? So this doesn't depend on the other functions that we have. And then in stage 2, the optimization algorithm that we chose is alternate optimization because the m and e hat depend on the g hat and h hat. So first you fix m hat and e hat to learn g hat and h hat, and then you freeze m hat and g hat to learn and h hat to optimize for your e hat. So this is just one we chose because it's a bi-level optimization problem. You can maybe choose some other ones. And I don't want to spend too much time on experiments because it works. That's why the paper is published. But basically, a few words we try on a small world setting and a larger cancer genomic atlas setting where we generate we generate semi-synthetic data sets that fits with the assumptions. So yeah, that's why it works. And the results are good.
What's the y-axis?
The yeah. So the y-axis is explained here. So so the y-axis is a metric to compare the Kate, and we compare it by taking by this weighted or unweighted expected precision in estimation of heterogeneous effects. So the weighted version would be you take the difference between your estimated Kate and the true Kate, square it, and then weight it with the propensity scores of the treatments. And the unweighted case would be you don't. Yeah. Okay. Yeah. So the SIN performs fairly well, unsurprisingly. So the take-home messages is that this is an algorithm that can take arbitrary treatments. You can have categorical or continuous or structural, high dimensional, whatever you want. The structures in the structural treatments don't have to be causal. So yeah, so like for example, so a structural treatment would be like molecules. So it has some chemical structure. So the point here is still that the only causal structure you need to be certain of is this 3-variable one, but you might have some additional structures in your treatment or your X or your Y. Well, Y is 1D here, but you don't need to care about.
So you say that the chemical structure of the molecule itself is structured in or what is, so there's no causal structure between the atoms in the molecule, or what is that? Or is this like completely what I mean?
Oh, so yeah, what I meant is that I just want to make clear the point that we don't need to be certain of causal structures in a very fine-grained way to use this method. So the chemical structures can be causal or cannot be causal, doesn't really matter for this algorithm. Yeah.
What happens if you apply this to like a very simple regression model? There's no causal structure, all the variables are independent. Would it perform at least as well as standard?
Oh, that's a
Like, I'm wondering, what are the edge cases for this model perhaps overfit based on the system of the structure, even if whether it's explicitly no structure, right? Would they all? Or the sparse construct, right? Very sparse construct. This model overfits in that sense, and assuming things are related, even though these things are independent.
I don't think it would overfit more than the other algorithms because.
Like a very less regression, certainly. No.
Okay, so the algorithm that we use to process the structural part is separate from the Robinson decomposition, generalized Robinson decomposition. So what thing you use there is your choice. So you can, so if you have a very simple variable, then you can just not use a neural network to do, or not use a very complicated black box function to deal with
I guess this approach where you already know this graph, right? And there's we don't know the structure, and then you have to infer it, right? So this example from that support suppose is where you already know the structure, so you can make an educated guess about the structure to use. Is that?
Oh, by structures you mean like chemical structures or whatever, right?
Yeah, structure data, I guess. Right?
Yeah, I guess, but that you can see, right? You know what data you have at hand.
Right, but for instance, the school example, right? We don't know what the causal structure is. We assume there's probably going to be some causal relationships, right?
Okay. So you need to know something about the causal structure, and what you need to know is, go back to that slide. That
Yeah.
you need to know that, yeah, you have some well, it's up to the practitioner to know what they're interested in as cause and effect.
Okay.
And then you need to know that you need to know this DAG. But if you whether the DAG is like that or like that doesn't matter. Yeah.
Right. So essentially it's some sub of interest, variables of interest. Has to mean.
Yeah.
Okay.
Yeah.
Right, but you're allowing for other possibilities.
Yeah. Mm-hmm. Yes.
You say you only need to know this part of the graph, and if there's other stuff around it, this is not necessarily required in the
Correct. Well, but
if you show here's the collider in this relationship.
yeah, exactly. Yeah. So
in other view that lies between A and Y, that those that A and Y, then this
exactly. So here we do make this conditional ignorability assumption. Yeah. Which needs to be relaxed. But I want to make the point that because I get the sense that when people see a graph, they're rather scared. But I just want to make the point that just you like assuming a 3-variable graph where you have this confounder just means that you need to assume that there is this confounder that forms this sufficient adjustment set that will give you the end causal effect. You can have some other variables, but of course, this is still a very strong assumption that we need to relax. Yeah.
I have a following question. So we need to make the same assumptions as in other methods. For example, in probability assumption, we have some overlap.
Mm-hmm.
My question is, what can you achieve with this method if you cannot achieve with, for example, propensity score matching or inverse probability of theory, where you simply make the same assumption?
Yes.
Or the double machine learning that you also cited,
Mm-hmm.
to me, it's exactly designed to solve this type of problem.
Yeah.
And I'm struggling to see what. Sorry if this comes across as the next question, but
No.
honestly,
yeah.
So what can you learn with respect if you put that toward the other?
Yeah, so that's a great question. So what I can say is that as far as we know, previous methods do try to use this with propensity scores, but they generally fall into 2 categories. One is they deal with binary treatments. So you have the fairly well-known Nian Wager, whose paper we extended. They basically do what we do, but with binary treatments. So that's why they use the propensity score, right? The propensity score, well, yeah, you can have multiple treatments, I guess, with you. Yeah. And there are also methods that deal with continuous treatments, but they usually deal with either one dimension, and the motivating example, for example, in double machine learning is a linear case. So with this method, we can do arbitrary treatments and we can do nonlinear estimation with fast rate.
My understanding was that the double machine learning works beautiful in that case, but I'm curious.
So I think that the first example in double machine learning is a linear case, right? Yeah. And later I think what they propose is this name and orthogonality condition that gives you fast rate, but they don't provide an explicit algorithm that can deal with high dimensional data doing nonlinear assumption, which we do in this case by not using the exact same machinery as double machine learning, because we also introduced generalized propensity features, which is not something that existed before.
So you mean high dimensionality also in the treatment?
Yeah.
Not only the...
Yes, absolutely. Yeah. Yeah. So high dimensional treatment, high dimensional confounder with whatever structure you want.
So A is a vector form.
Yeah. Yep. So great. Thanks for the question. Let me go back to. So are there more questions? So now is also a natural pause point. So, okay. Would you like me to stop the recording?
Could you provide a sense for the scaling of these, I think in all lines for, I think you have some graphs, what kind of products are practical in this as you read the experience?
So this would work well if, as we discussed, you assume conditional ignorability. So you assume you know the confounder. And then I think this can work fairly well if you're, yeah, so in the example I gave, if you want to process some practice essays, and then you have good faith that that teacher's report is a fairly precise description of the confounder. Whether it would work well in the very low dimensional case, whether it would work better, I mean, than other methods in the very low dimensional case, like Charlie pointed out, I'm not sure. I'm not sure if it would work like necessarily better. Yeah.
I'm just interested to get the idea of how long it takes to train the model for these practical cases that you shall show me.
I don't know, because I wasn't responsible for experiments, but I can email you later.
Right. Yeah. Okay. We make a invoice and
yeah. So in the previous method, we needed to use we need to use the assumption that we know the confounder. We need to assume conditional ignorability. So now this next work is with the aim of relaxing that. In particular, we're going to use this. We're going to introduce this concept of proxies, which is a corrupted measurement of the confounder, and we'll achieve non-parametric estimation with kernels. Okay, so again, first I want to introduce assumptions. So again, we take the rate retention as a running example. So here, of course, cognitive ability is something that's not observed. But what we then hope for as one step weaker than observed cognitive ability is to assume some other covariates with it, which we can reasonably say to account for it. And this is what we need. We need 3 other types of variables. Yes.
There use as teachers records, but was also a proxy for the real thing.
Yeah, definitely. So that's a very good point. So the difference is that in that case, the answer is that it depends on the quality of the proxy. So if the proxy is so good that there are, so as I will illustrate in this graph. So in this graph, it makes it very clear why the proxies themselves are not sufficient, because you still have this backward path from A to U and to Y that's not blocked. But if your proxies are good enough so that it blocks all of them, then you can just use it. Okay, so Okay, so we need to be able to split the covariates into 3 categories. So first, the first category is observed confounder. So the confounders are, so all variable here are generated from U. The observed confounder will be will be a causal parent of both A and Y, causal ancestor of both A and Y. And then the other 2 types of categories are separated into this Z type variable called treatment inducing, which is on treatment side. So for example, elementary school scores can be used as a can be reasoned by social scientists to cause to be a good predictor of whether the students needs to repeat grades 1 or 2 years later. And kindergarten scores is often used as a measurement of the IQ, basically, which is like a long-term indicator of how this person would do in the long term. So kindergarten scores is on the other side, is on the outcome side. So this is called outcome inducing. So we need to be able to separate a bunch of covariates that we have, which we know are proxies of the hidden confounder, and we need to be able to separate it into 3 categories: treatment inducing, confounder itself, and outcome inducing. And formally, they need to satisfy this graphical condition. So conditioned on U and X, essentially, like U and X needs to kind of separate Z, A, and W, Y. So formally conditioned on A, U, X, Y is independent of Z, and conditioned on U and X, W is independent of Z and A. So now, of course, the proxies, we can't use anything as proxies. The proxies need to be sufficiently correlated with U for them to act as good enough proxies that can still recover us the causal effect. And this, how good they need to be is formally characterized in this completeness condition, which is in this paper. And here the target quantity we want is the average treatment effect. So we've gone back from Kate to just ATE, average treatment effect. Okay. So first, to give some backgrounds in how to identify the ATE from these variables using the conditions. So again, I think the linear case is a good way of illustrating. So in the linear case, I write Y as a linear combination of all of its parents plus noise. And W is, again, a linear combination of parents, which are just U and X, given some other exogenous noise. And then now I consider conditioning Y and W on A and the other proxy, Z and X. And with that, I'll realize that A and X become fixed, and then I have to take the conditional expectation of U given given A, Z, and X for both the Y case and the W case. And now, by exploiting the fact that these 2 coefficients are generally different, by exploiting the fact that these two coefficients are different, I can substitute for my expectation of U given AZ and X for expectation of Y of W given AZ and X in this top equation. And then I realized that now the expectation of Y given AZ and X is just still a linear combination, and now it's a linear combination of A, X, and this the expectation of W given A, Z, and X, but with some different coefficients. And where, importantly, the coefficients of A is not changed. Okay, so now what I realize is what I can do is I can first regress W to A, Z, and X, and I call that, let's say, W hat, which is just like a function of A, Z, and X. And then I can identify this this coefficient A, beta of A, by regressing Y onto AZ and X, or you can call it AX and W hat, which is a function of AZ and X. Okay, so in the linear case, and now, so of course this is for the linear case, and I also want to do it for the nonlinear case. So to introduce that, I want to write y, like starting from this function, expectation of y given AZ and X. I realized that I can also write y as just a function of the same function here, plus some noise epsilon star, where epsilon star is independent, where epsilon star is uncorrelated from AZ and X. Okay, so I generalize this to say that, well, all I'm doing is just that first, I just want to be able to like regress both y and H linear to AZ and X, right? And I want to regress both of them to AZ and X so that the regression, so that the expectation given AZ and X are equal. And once I can identify the H linear, I have basically identified the causal effect. If I really want the causal, if I really want to isolate this beta A, I can just marginalize over my W and my X. So this is what we do in a nonlinear case. So so H, so in the nonlinear case, this H called a bridge function is a nonlinear function such that its expectation given AZ and X is the same as the expectation of Y given AZ and X. And if we can identify the H from there, we can get the causal effect by marginalizing over the marginal distribution over W and X. So yeah, so in summary, to get the target function y given to A, we basically need this H. And where is H from? H comes from solving this integral equation. So the expectation is just an integral. Solving this integral equation of y minus H given AZ and X. And we want to solve for H as a function of A, W, and X. So how do we do that? So that identification result is not it is previous work done by other people. But to solve for this H, right, from this integral equation is itself a non-trivial problem. So how do we do that? We're going to the tool we're going to use here is kernel ridge regression. So first I want to have a brief introduction to it. So I think the easiest way of understanding kernel ridge regression, at least on an intuitive level, is to look at it, right? Like in analogy to featurized regression. So featurized regression is just that you would assume that F is a linear combination of some finite dimensional feature vectors of X, and then the goal is to identify this theta, and theta star is done by taking the argmin of just this ridge regression objective, taking the square difference between the function and the labels, and then with the penalty on the size of the vector theta. This is basically almost exactly the same in the the idea is exactly the same in the case of reproducing kernel Hilbert spaces, where instead of saying F is an inner product between some finite dimensional vector theta and some finite dimensional feature vector phi, now we make phi to be the kernel features, which is an element in the RKHS, and we take when we embed F in an RKHS, F has this property where F itself has is an element in the RKHS, and the evaluation of F at X is just taking the inner product between F and the features at X using the RKHS inner product. So F. So how do we identify this this F? Well, we also do this kernel ridge regression, which is analogous to ridge regression, which is just that we take the argmin over F in the RKHS using this objective. That's the square difference between the labels and the evaluations of F at X, and with this ridge penalty that comes from taking the RKHS norm of F. So yes, here you might have a question like this would be an infinite dimensional, a potentially infinite dimensional space. So how do we even represent this F, right? This, thanks to the representers theorem, the F that comes from this would just be a finite linear combination of the kernels centered at the sample points. Okay, so now I want to use what I just said to estimate for this H in my proximal causal learning setting. So I'm going to embed H in an RKHS, and the H evaluated at A, W, and X is just the just the inner product between H, the RKHS element, with the features at A, W, and X, right? So there are three inputs. So I take the tensor product between these three feature vectors. And yeah, so this is how I represent H. So but as like from this equation, I also need to be able to represent the expectation of H given A, Z, and X, right? So how do I take the expectation? So under suitable conditions of the kernel, I can start from this inner product, and then I can move the expectation sign in. So because this entire process is linear. So I move it in, and I realize that the expectation of H given AZ and X is just still an RKHS inner product between H and features of A outer producted with features of X, and outer producted with this expected features of W given AZ and X. Okay, so now the problem boils down to being able to know what is this expected feature, which is which in RKHS language is called mu. So it's the conditional mean embedding mu. So I know how to represent a function, and I know how to learn it. So now how do I represent this conditional expectation of functions, and how do I learn it? So again, this is analogous to finite bases. In finite bases, I still have this F represented as a linear combination of features. Then the expectation of F is just still theta times the expectation of features, right? So how do I learn the expectation of features? Well, this can be posed as like a multi-dimensional to multi-dimensional regression problem, where where the ridge regression is between is where the labels in the ridge regression is the features of X at the Xi's, and then I want to regress it from the phi of Zi's, and this big theta here would be a matrix. So the output of this thing is like the predictor of the phi X under this decomposition. So here I'm taking the vector norm. Okay, and in the RKHS case, I instead of like basically this thing, this phi of X becomes infinite dimensional. And how do I learn that? So without going into the details, it's sufficiently intuitive to know that the same kind of thing works. So you just basically from pulling a kernel ridge regression with 1D labels, you pull this where the labels are also infinite dimensional. And this also comes out with a finite linear combination representation. Okay, so now I have told you how to learn how to learn age as a function and how to learn the expectation of age. So now this gives rise to our algorithm, where we want to find the age that satisfies this equation. We do this in 2 stages. In the first stage, we try to learn the conditional mean embedding by regressing from the features of A, X, and Z to the features of W. Once we have got this conditional mean embedding, remember the expectation of H given A, Z, and X is just H inner producted with this, and this conditional mean embedding. So we replace the analytical conditional mean embedding with the sample one. And then to identify H, we now regress using stage 2 kernel regression from phi of A tensor product, phi of X tensor product mu to Y. That'll identify the H. Now this under suitable conditions specified in the paper. So the key ones are H needs to be an RKHS function, and we need to use a characteristic kernel. This KPV, so this algorithm provably converges. We do this on synthetic and semi-synthetic experiments. Shows that empirically it also works reasonably well. However, empirically, when you have higher dimensional treatments and proxies, this method does not scale super well. And the reason is that although there is theoretical results, this method still uses fixed kernel features. So empirically, it does not do as well as if you learn the features using neural networks, which is in an extension work by Xu et al. Deep proxy causal learning, where the kernel features are learned, where instead of using kernel features, the features are learned using deep neural networks. Okay. So the take-home messages here is that this is an algorithm allowing nonlinear treatment effect estimation under unobserved confounding with theoretical convergence rates guarantees. The conditions are considered weak because only partial knowledge of the graph is needed, and you don't need this restrictive assumption like the IV needs to be independent of the confounder. Here, all of the proxies can be correlated with the confounder, and you don't need to know the graph structure within each of the proxies. So the proxies can themselves be multivariate. You don't need to know how they're structured. Yeah. Okay, so now is also a good time to take questions. So in the proximal causal learning with kernels section, we relax the observed confounding condition, which is good. But of course, in social sciences, many variables are not fully observed or are only measured in an imprecise sense. So the next goal is to generalize this relaxation of observability to more variables. And that motivates this work. So the third part of this, the final part of this talk is titled Causal Inference under Treatment Measurement Error. So where additional to assuming unobserved confounding, we also assume unobserved treatments. But with the corrupted measurements. So flashback to this previous slide where the mastery is only measured via exam results as an imperfect proxy, an imperfect measurement of it. And you remember that this masks interesting relationships in the true structural function. So how do we deal with this? So in this work, we need to assume the following. First, I need to have two measurements of the treatment, and I should motivate the example here. So here I'm using this example where this A is like the variable that represents some kind of mastery of scientific subjects, and let's say we're interested in its effect on like long-term career outcome, and these two things are confounded by one's domestic background or some other variables that you can't fully observe, or like it could be aptitude and so on. And what we want is the average treatment effect, again, expectation of y given do A. So now I need to do this when the A is corrupted, I need two conditionally independent measurements of A subject to additive noise, where the noise, the noise in the measurements can take arbitrary distributional forms. So it does need to be additive, but the added noise can be arbitrary themselves. One of them needs to be centered at 0, and the other can have a bias as well. So this admittedly are strong conditions because, like, yeah, we need two measurements and they need to have this additive noise structure, conditionally independent, but this is what we have for now. So from here, there is this old result by this guy called Kotlarski that says that if you have two measurements, two conditional independent measurements of this form, then you can identify the characteristic function of your latent variable via this formula, where the left-hand side is just the characteristic function of A, of the variable A. So characteristic function is just the expectation of the Fourier basis under the probability measure. And on the right-hand side, this says that you can identify this from the right-hand side, which only contains variables that you see. So on the right-hand side, so it's this rather complicated function, but I'll explain it term by term. The top here is rather complicated looking, but it's still a function of the characteristic function. It's a function of the characteristic function of M and N. But differentiated, which means which is why it takes this form. And the bottom of it is just the characteristic function of the variable N. So what this result is saying is that from the characteristic functions of N and M and N, I can identify the characteristic function of A. And because there's a one-to-one bijection between characteristic functions and probability distributions, that just means I can identify the probability distribution of A. Okay, so but this is not enough though, right? Because I don't just want to know the marginal probability distribution of A, because I still have this confounder to deal with. If I fully identify A back, then I'm back to the 3-variable confounded case with an unobserved confounding, and I still need something else to identify it. So from this, so in this case, I am going to extend from this instrumental variable algorithm, which yes is restricted, but later on I will give a scenario where this can actually be used. So yeah, so to remind you, the identification comes from assuming this additive noise model where the y given due is just the f itself, and then f is a solution of this ill-posed integral equation, where so exp of y given z is just the exp of f of a given z. So how to do this? So immediately, this might have already reminded you of the previous module about identifying the h, right? The story, the structure looks rather similar. So in that case, we need to identify h, which is a function of aw and x, by conditioning it on az and x. So conditioning it on something that's different from its input, and then comparing it with y, conditioning on the same thing. And here we kind of have the same story, right? We need to identify f by conditioning it, by considering its conditional expectation on z, which is different from its input. And we also want to compare it with the analogous expectation of y given z. So so we can pull the same trick. If A is observed, we can pull the same trick and say, if f is in an RKHS, then f is this, right? F evaluated at A is just f, the function, inner producted with the RKHS features at A, taking the RKHS inner product. Then this right-hand side simplifies to, so the left-hand side is the same, and the right-hand side is just this, but you take conditional expectation of phi of A given Z. So this thing is, again, the conditional mean embedding. So now we want to use the conditional mean embedding of A given Z. And you can already imagine two-stage procedure, right? First I want to regress Z to A to identify this mu of A given Z, and then I regress this conditional mean embedding to Y to identify my F, except A is not observed. So if A is observed, then we can just do this. But now that A is not observed, so how do we still identify this CME, right? So this mu. So the bottleneck lies in identifying this mu. If we can identify the mu, we can identify F. So to do that, I'm going, because I'm extending the IV algorithm, I assume that I have an IV. So this IV is, let's say, the school runs this policy of increasing scientific project components in class. Then note that because this Z is completely exogenous, so I can very cheaply add it in to all of my conditional expectations in this formula. And the thing still holds. So to understand why this is true, just imagine a world where you just set Z to a particular value, and then you run the rest of it, right? Then in that snapshot, this thing would hold. So like immediately once I very cheaply added it in, I basically, then this formula tells me that I can identify the conditional characteristic function of A given Z from the conditional characteristic functions of N given Z and Mn given Z. But of course, I don't just want the characteristic function. I actually want the conditional mean embedding, right? If I get the conditional mean embedding, I just run a stage 2 regression, and then I get my F back. So now in this paper, we show that we can build this bridge between characteristic functions and conditional mean embedding. So note that, and the way to do this is to note that, remember, we get the conditional mean embedding from kernel ridge regression, from like high dimensional kernel ridge regression. And ridge regression gives us nothing but a linear combination of features. So it turns out that the conditional mean embedding of some variable X given Z, just in general, so not this is not about the given problem, just that if you observe X and you observe Z, if you want to run this KRR, and then the mu you would get out of that is nothing but a finite linear combination with coefficients gamma, hat, and j of the kernels centered at the xj's, where this gamma is this number get from kernel ridge regression, which looks analogous to a standard ridge regression result, right? So now I'm going to construct an estimator of my characteristic function using the same gammas, but this time, instead of weighting the kernel centered at xj's, I weight the Fourier bases. And the intuition is that the expectation of characteristic functions should be some kind of linear sum of Fourier bases, because car functions comes from taking the expectation of Fourier bases. And the theorem one of this paper is saying that if we choose a translation invariant and characteristic kernel, then the mu's are going to converge to the true mu if and only if the characteristic function converges to the true characteristic function in the measure given by the inverse Fourier transform of the kernel. So I get that one converge if and only if the other one converge, and they converge at the same rate as well. So if I get one, I get the other one. Okay, so this is great. So basically what this means is just that I again start from this equation that's supposed to give me the characteristic function, right? So basically all I need to do is to come up with an estimate of each of these is to come up with an estimate for each of these terms, the analogous kernel conditional mean embedding. And I can do this, right? Because for the right-hand side, all of the variables are observed. So I run kernel ridge regression of n on z, and I run kernel ridge regression of mn on z. That gives me the mu of n given z and mn given z. And along with the mu hat, I get the gamma hats resulting from when I do this KRR. And I take this gamma, and I just use this gamma to construct an estimate of the characteristic functions. And that gives me a sample estimate of the right-hand side. And from the sample estimate of the right-hand side, I run this equation, right? I just perform this equation, and that gives me a sample estimate of the left-hand side. I'll elaborate how to do that later. And once I have a sample estimate of the left-hand side, which I will get of this form, I again just grab my gamma hats from here and plug it back to the analogous CME formula, and that'll give me the an estimate of the CME of A given Z. And once I have that estimate, I plug it in to stage 2 of kernel ridge regression, as in the previous case, to get my F. Okay, so to elaborate, how do we obtain the estimate of the characteristic function? So here the pain point is that even after replacing each of them with a sample estimate, I still have to take this integral, and then I take this x, which still feels like a lot of computational work to do. So ideally we don't want to do that. So what we do is that we first take the log of both sides to remove this exponent function, and then we differentiate basically with respect to alpha to remove this integral. And after we do that, we're going to end up with equation 2, where the left-hand side, as you can spot, comes from first taking the log and then differentiating. So that gives you this ratio form. Okay, and then once I have done that, I replace each term with sample estimates, which for the right-hand side, I can get from sample estimates of my mu. And so I replace the sample, I come up with my phi hat ends of the right-hand side from first doing the mu's. And then once I have done that, I get the phi hat n of A given Z of the left-hand side by first assuming the form of the phi hat ends, right? Which is just gamma, a linear combination of the gammas multiplied by the Fourier coefficients. And then I find the gammas by minimizing the discrepancy of the two sides of the equations. Okay, so to summarize this algorithm, basically in step 1, we run KRR to come up with these mu hat of n given z and mu hat of mn given z. We do this because we observe all of the variables here, and once we get them, we just grab the gammas out and then plug it into the corresponding formula for the phi hats, and that gives us a sample estimate of the phi hat n given z and mn given z. And once we have done that, we minimize the two sides of that differentiated equation to come up with a sample estimate of the phi hat of A given Z. And once we've done that, we again grab the gammas out and then plug it into the analogous equation of the mu hat n of A given Z. And once we have done that, we're done basically. And then previous work does it for us. We just take the mu, the sample estimate of the mu of A given Z, and that gives us the F by doing KRR again. Okay, so So experimental results shows that our method performs quite well in synthetic experiments. So we try to vary the amount of measurement error, and we note that our method does especially well when there is large measurement error compared to naive baselines, which just takes the observed measurements as a stand-in. And here the oracle is basically the two-stage algorithm with the true observed measurement. Okay, so the open questions of this is, so admittedly, the conditions of this method is rather strong. It relies on the IV assumption, and it relies on additive measurement error assumption. So it would be good to for example, if we can relax the IV assumption to like maybe only use proxies, that would be weaker. And also this currently only deals with the static setting, which is actually also true for the previous two methods. So for social science use, it would be quite relevant to extend this to sequential setting. And the take-home messages is that non-parametric features can be learned even using corrupted measurements. And this algorithm relaxes observability conditions from confounding to even allow corrupted treatments. However, IV is a restrictive assumption for observational studies, but it can work for studies with an experimental component. And an example of this is if the school has the means to say, we're going to increase the science project components now. So conclusion for my talk. So I talked about causality for social sciences from a high-level perspective. Why is causality suitable for social sciences? Because in social sciences, we care about decision-making rather than correlation observing. We care about exploiting observational data, and we care about correcting spurious correlations. And secondly, causal graph can be viewed as a way to encode expert knowledge, which can be hard to learn with pure data. Where I made the point that graphs can have a spectrum of restrictiveness. And thirdly, observability conditions can be relaxed at various degrees. So this concludes my talk. Thank you very much for listening and for staying the full nearly 2.5 hours. Very much appreciated. I will stop the recording now.